Hello, everyone. I'm Laleh Golshahi, and it's my pleasure to speak with you briefly about the research happening in my research group, which I affectionately call Respiratory Aerosol Research and Education at Laboratory. I'm an associate professor in the Department of Mechanical and Nuclear Engineering, and I will be talking to you briefly about some research background material related to respiratory deposition of inhaled aerosols. And then we're going to briefly look into some active areas of research, and then I'd be happy to answer any questions that you may have and any follow-up conversation as you're considering your exciting journey to start your graduate studies in our pharmaceutical engineering program. The type of research in my laboratory is translational science. We are interested in coming with in vitro platform that are anatomically correct and they're biorelevant, and they will be able to shed light on quantifying deposition at the site of interest. Currently, as you may know, the in vivo studies, they're mainly qualitative studies, or also we also have PK/PD, but for locally acting drugs, it's important to know the amount of drug reaching the site of interest. Those inhaled aerosols could be unwanted aerosols, such as viruses, but they could also be wanted aerosols, such as the aerosol emitted from pressure emitters or inhalers that you've likely seen asthmatic subjects have to use them regularly. As well as nasal sprays, for example, for the application of nasal drug delivery. So as simple as all these devices may look like, the inhalers, for example, or the nasal sprays, the physical rules governing the deposition of the aerosols, they include the effect of, they need to account for the effect of the aerosol's size distribution as well as the inhalation pattern, meaning inhalation flow rate and how fast they reach the maximum amount, as well as the anatomical aspect of the airways. So these in vitro platforms, they give us the sort of laser focused view into the morphology of the airways as well as the dimension of the airways. And those are advantages in terms of coming up with personalized approaches for drug delivery, as well as basically being able to use them to come up with optimized methods of drug delivery, for example, for targeted delivery to the sites of action for locally acting drugs, for instance. There are different various applications. They could be used for even understanding the amount of nicotine reaching the lungs and how the device and device setting could affect the amount of nicotine, for example, which is a more recent area of research in terms of ENDS, electronic nicotine delivery systems, as well as, for example, high flow nasal cannula therapy with the cannula, as well as even research in terms of delivery of drugs for the COPD disease and for sleep apnea. Oxygenation is important. So these models, they have plenty of capability in terms of understanding the deposition of the aerosol and coming up with approaches to optimize delivery to the target. In terms of main areas of research, the active area is in vitro in vivo correlations, or IVIVC, as the FDA and regulatory agencies call it. And the focus is on OI and DP, orally inhaled and nasal drug products, and they could have various sub-umbrellas of sub-areas of respiratory drug delivery, which includes nasal delivery and pulmonary drug delivery, as well as I briefly discussed some research interest, recent research interest in terms of electronic nicotine delivery systems and high-flow nasal cannula therapy, and how the device and the flow rate and the subject variability may all affect the final outcome. This is an example of the process. Basically, we start with the CT scans, convert them to models, and these computer-aided design models or CAD models, they could be converted into 3D printed models, and we can use them for various applications. For instance, in this case, we're looking into the effect of the age effects, and as well as comparison of the regional deposition of various types of nebulizers. And the opportunities are endless. In terms of nasal drug delivery, the application doesn't limit to the locally acting drugs. They could also be used to look into vaccine delivery. Obviously, we are always working on increasing the biorelevance of these models, especially for the vaccine application, for example. We'll be able to account for the tissue and the surface of the model being more biorelevant. And these are mouth-throat airway models. So basically, this is the opening of the mouth or the lips, and this is the trachea going to the lungs. And as you can see, the subjects are quite different from one another depending on how they form their mouth around the mouthpiece. So these platforms allow us to capture intersubject variability as well as looking into different areas of interest depending on the applications. And obviously having those biorelevant platforms, they allow us to optimize gas and drug delivery depending on different applications. For example, we could look into the mouth-throat application mouth to lungs application, or we could look into, for example, improving oxygenation using the cannula, and being able to look into smaller airways, even this is a bifurcation of the airways, and being able to look into the regional delivery of the drug, for example. As for the potential projects within the next 3 to 5 years, we're working on, as I mentioned, biorelevance of these airway models, and as the biorelevance is improving, we're also looking into age-specific devices, mainly considering pediatric geriatric subjects, and the targeted pulmonary drug delivery, and how the science of how these understandings of physical aspects would optimize our targeted approaches, especially for the acute diseases. As you've been familiar recently, we need to be able to deliver as much as possible with the consideration of minimizing toxicity. So these platforms are mainly needed for saving time and being able to prevent any type of side effects. And obviously these platforms could also be used for the other side of the spectrum, how to understand the position of unwanted aerosol, inhaled viruses and toxic aerosols, pollutants, and allergens, and how to be able to come up with preventive measures and avoiding their deposition. As for the current team members, we're relatively a small group. Our postdoctoral fellow is Dr. Amireza Ismaili, and one of the pharmaceutical engineering graduate student, Arya, is one of our pharmaceutical engineering graduate students. And as for the alumni, we've recently had a successful group of addition to the workforce. Dr. Ali Al-Faifi has recently left us to Recode Therapeutics as an aerosol scientist. Dr. Michele Dario Maniello is in a research position in Italy, and Dr. Sana Hosseini, who was my first graduate student, is currently a senior scientist at Ceron Bioscience in Oregon, and Dr. John Wilkins, currently a lecturer at VMI. With that, I'm going to keep this video as short as possible, and I'm happy to answer any of your questions. Please feel free to reach out to me by finding my email on MNE Mechanical Nuclear Engineering VCU website, and I look forward to be able to meet you in person at some point. Take care.